Ayush Prasad. Now, in this episode, we are going to be discussing about Maxwell's equations, the equations that govern all of electricity, magnetism, and light. Sounds exciting, doesn't it? Well, let's dive right in. Actually, before we do that, we need to answer a quiz question from last episode. Hans Christian Ørsted got a unit named after him, the Ørsted. But what does this unit measure? And more importantly, why isn't it a standard SI unit? Well, the Ørsted measures magnetic field intensity, which is a fancy way of saying how strong is this magnet. Now, we're done with that. On to Maxwell's equations. These are Maxwell's equations. What is this? These are Maxwell's equations. Well, you might recognize this chart if you're an avid viewer of this channel. It was featured in our last episode on divergence and curl. Now, this diagram shows what divergence means. Now, what it essentially means is how much the field is going out of a particular point. A field is just arrows everywhere, and the divergence of field is how much of those arrows are going out. Here, all the arrows are going out, so there's a positive divergence. Here, the arrows are going in, not out, so there's a negative divergence. Here, the same amount of arrows go in as they go back out again. So, it has zero divergence. Now, let's talk about curl. If I just flip this whiteboard. Yes, so this is our chart about curl again from last episode. Curl basically measures how much the vector field would spin the paddle if a paddle was placed here. If it spins it counterclockwise, the curl is positive, and if it spins clockwise, it's negative. Why? Some scientists decided that a long time ago, okay? Don't argue with them. Anyway, as you can see here, the paddle is very obviously going to turn counterclockwise. So there's a positive curl here. But what about here? It doesn't seem like there's any curl here, but look, the arrows here are larger. They're moving faster at the top here than the bottom. Actually, this was caused the paddle to spin clockwise until it rests flat. So this has a negative curl because clockwise is negative. Now that we've quickly recapped divergence and curl, we can move back to Maxwell's equations. Now here we have the four Maxwell Heaviside equations. There used to be 20 equations which were invented by Maxwell. But then a guy called Oliver Heaviside came along and made those 20 equations into 4. And these are the 4 you see here. He actually invented a new field of mathematics where he did that. It's called vector analysis. Anyway, all of these have fancy names. There's Gauss's law for magnetism, which is totally different from Gauss's law. Then you have the Maxwell Faraday equation and Ampere's law. Now, don't let the fancy names and fancy symbols fool you. They're very simple. First, we need to explain what all of these mean. This upside down triangle is called nabla. Nabla with a dot next to it means divergence. Nabla with an x next to it does not mean multiplication. It means curl. So what nabla cross B means is the curl of B. What is B? E means the electric field. B means the magnetic field. Why is it B and not M? I have no idea. Now, this thing over here is a Greek letter, and it stands here for charge density. And this letter J here stands for current density. Charge and current, if you didn't know, are very different things. So watch my first episode on electricity to explain what they mean. Finally, this weird looking D. This curly D is actually the letter del. Del something by del T just means how much that something changes over time. So del E by del T means how much the electric field changes over time. Now that we got all the symbols ready, we can actually start looking at each one of these equations. Now, you might think we'll go through all of these in order, but we're going to go through them in order of simplicity. Let's start with this one, Gauss's Law of Magnetism. This states the divergence of the magnetic field must be 0. What does that mean? Well, it basically says the magnetic field, arrows cannot jump out of one point or drain into one point. They can only go in loops. Now, I'll make a quick diagram of the magnetic field. So imagine that this is a north pole and this is a south pole. These arrows go from the outside into the north pole and go all the way back to the south pole, and then they go out. So they connect back and form a loop. So if you look at one of the arrows here, it goes in to the north pole, goes all the way to the south pole, and goes back out again in loops. Here's the thing. The magnetic field can only go in loops. This is what Gauss's law of magnetism states. You can't have them jumping out of one point without coming in somewhere else. So, what this means is that you can't have a north pole without a south pole, and you can't have a south pole without a north pole. Think about it. If there was a north pole without a south pole, there would be nowhere to complete the loop, which would violate Gauss's law of magnetism. Therefore, a single pole, what we know as magnetic monopoles, cannot exist. They won't. Ever. Interestingly, some physicists have shown that during the Big Bang, where physics and topology were weird and wacky, magnetic monopoles could have formed and stayed the same for billions of years and reached today. But that's a whole other field that we won't get into. Now, let's talk about the next law, Gauss's Law of Electricity. Look, my marker has magically changed color. Magic. Anyway, Gauss's Law of Electricity. It simply states that the divergence of the electric field is equal to the charge density at that point. So basically, what that means is that if you have a positive charge and a negative charge, since these are positive, the divergence is positive. So the vector field would come out of these points. Let me quickly draw that. Since it's negative, the charge density is negative, which means the divergence is negative. So from here, the field would come back in, so to speak. So what this simply means is that electric field lines, as they're called, start at positive charges and end here at negative charges. Here's the thing. Unlike the magnetic field, you can just have a positive charge in the middle of nowhere without any negatively charged friends. All the lines would just be going out of it forever and ever. This is a key difference from the magnetic field, where every pole has to be coupled to an opposite pole. Now, the next one is the Maxwell-Faraday equation. What this simply means is that the curl of the electric field is equal to the opposite of the change in the magnetic field over time. And what this means is that, I'll try to draw in 3 dimensions here. If you have a magnetic field that is changing over time, look, it was small here, now it became larger. So this means that the change is positive, which means that the curl will be negative. And what this means is that if this is the magnetic field B, the electric field will go clockwise around it. I've drawn it counterclockwise here, but still you can see that in a changing magnetic field B, the electric field curls around it. And this is actually how most of your power comes from changing magnetic fields. Now the final law we'll be discussing is Ampere's law. It's pretty complicated, but don't worry, you can easily understand. It states that the curl of the magnetic field is equal to the current density plus the change in the electric field. What does this mean? Well, suppose that there is a current running through a wire. This is a wire and current is flowing to it. Now in this case, the curl would be equal to the current density. Since the current density is positive in this case, the curl would also be positive. And again, it would curl around the wire. And this is actually counterclockwise now, not like the one we did earlier. The second reason there could be a curl in the magnetic field is that if the electric field is changing, which could interestingly be an alternating current in the wire. So since the current is oscillating, the curl would also start to oscillate. This principle over here is actually how transformers work, but we'll talk about that later. Let's do a quick recap. We started off with a summary of divergence and curl. Then we talked about the Maxwell Heaviside equations, covering each 4 of them: Gauss's law of magnetism, the Faraday and Maxwell's equation, and Ampere's law, with nice, simple summaries. And after that, in our next episode, we'll be talking about how all of this relates to how you get your power and how you see. Now, wait till next time. For now, I leave you with a quiz question. I said at the beginning that particle physicists have found out that magnetic monopoles may actually exist, violating Maxwell's equations. Your challenge is to figure out what scientists call these magnetic monopoles. Clue: it's something very silly and funny. Until next time, this is me, Ayush, from the Funtastic Academy.